All right, so the next topic that I want to talk about, this is topic 12, if you're playing along on the website. The next thing I want to talk about is sampling. And this is going to be a very, very kind of powerful technique that we're going to use pretty much for the rest of the course. And so it's worth kind of figuring out exactly what we're talking about when we mean sampling, because we can have deterministic samples, random samples. And so first I want to start off with this idea of a deterministic sample. And a deterministic sample just simply means picking a sample that is not random, that there is some kind of algorithm or some way of picking that sample. And so why do we want to do this? We want to do this because the big part of data science is that we want to make conclusions based on data and random samples. And so kind of the overarching theme for kind of the next few lectures and kind of the course in general is that we don't generally know the entire population, right? It's either we don't know the values of an entire population, it's too costly to get some piece of data on an entire population. And so what we're going to do is that we're going to, instead of asking everyone in the entire country who you're going to vote for, we're going to do this. We're going to draw conclusions based on random samples. We're not going to ask the entire country who they vote for, but we're going to ask a random sample, a random selection of that. And if we do it right, we can make inferences about a broader population with some kind of confidence interval. And so that's kind of the roadmap for the next part of the course. So as far as the terminology goes, if we think about our table, if we think about our data in terms of tables, and we should, because that's kind of how we're representing data in this course, each row of the table represents an individual. Okay, so every row represents an individual of the population. Each column is going to be what statisticians call, and what we're going to call a variable in this course. And so I want you to think of the variable as some feature of the data, and literally mapping it to kind of our tables. It's a column. It's a column in the table. And so it's a feature, other people, I like to think of it as attributes. It is attributes for that individual. So each individual is going to have values in those columns. Each of those values represents a particular feature of one or more variables in our table. Okay, so rows are individuals, columns are variables, and we're trying to model an entire population. And the population is basically the set where we're going to draw our samples, right? Think a country, think Vassar College, think there's some population that is defined. And we're going to draw samples from that population. And each of those samples will be an individual with variables. Having the values for that individual will be those features. Okay, so that's kind of the general terminology. And so how do we pick which individuals from a population are we gonna that we're gonna sample? Well, one way you can do that is we can do that deterministically. And what that means is that it doesn't involve chance, that there is it is predictable about who we are going to sample. And we've done this, right? This is not new to us. Whenever we take a particular row of a table via the take method, we are doing a deterministic sample. We're saying, give us row 5, give us row 27, give us rows 2, 3, 4, 6, 7. And we also do that with where, right? This is deterministic. We're putting some condition on which individuals we take from the population, right? And we're looking at some variable, some feature that we're selecting on. But we're doing that very deterministically, right? If we had the same table of data and we do the same where clause, we're going to get the same data back, whether we run it, once. The first time is going to equal the second time equal the 10,000 time we've run that where selection, right? Assuming the population hasn't changed. So that's deterministic. We can also sample using probability. Okay, and so what that is before we draw our sample, we're going to draw up our sample. We can divide into groups, and we've seen that with the group method on tables, right? But if we have a population and we have some way of grouping them, we may draw from this table not where every row has an equal chance of being selected. We can divide our population up into groups, say males and females, or different age brackets, 10 to 20, 20 to 30, so on and so forth, right? Any way you want to slice up your data. And if we do a probability sample, what all that means is that within a specific group, we're going to pick from that group with a certain probability, okay? And those probabilities don't have to be equal across the groups. Sometimes you want to overrepresent a certain population. Because in surveys, right, this happens a lot where sometimes you have groups that are just, reluctant to do surveys, and they tend to be underrepresented. And so if you want, from the broader population, people who respond to surveys. So you may want to actually, when you're kind of drawing from your population, you may want to weight those groups more heavily to get a fair representation of what the actual population is. Okay, so that's a probability sample. But you do that beforehand. You say, okay, from this group, we're going to pick 60%. And from the other group, we're going to pick 40% from there. And so that's probability sample. We can draw samples with replacement, and what we're going to do then in that case is with replacement, you're always choosing from all items in the array, right? This is the equivalent of picking out a name from the hat and then putting it back in from there. And it turns out we tend to do this simply because it's a little computationally faster from doing that. And kind of the sneak preview is that if our population is large enough, sampling with replacement it can kind of converges without replacement. And so we typically kind of do samples with replacement from there. But we can also draw without replacement. And then again, that's once you pulled out an individual, you're not putting them back in when you draw another sample. And then you can do systematic sampling. And so what that means is that one way to think about that is you pick a row at random of our table, and then just give us the next 10 rows from that, okay? And then once you've kind of made that random selection, then pick every 10th row after that, right? The key here is that it's systematic in the sense that you've kind of predefined what you're doing, but it is random because you're picking the first row at random from that sample. Okay, another type of sample, and this is we listed it, but this is one that you probably should not endeavor to do too much, and we call this the sample of convenience. So imagine you're doing a survey, and you basically just you hang out on a street corner, and you get whoever walks by. And you think, right? So, I mean, and I don't want to be too harsh on that, right? That can be a useful technique, but you have to be careful because you have to be careful if you think of it as random. Because if you think you're sampling at random, well, it doesn't, because it also depends on where you are in the street, what time of day, for that. A great example of this, of kind of random sampling. Unfortunately, I don't remember exactly where I heard this story, but it's too good a story kind of not to tell you. But Vassar's motto, go to the source. I can't actually tell you the source of this, but even if it's not true, it's kind of a cool, it's a fun kind of example story. So there's this research lab, and they're doing, there's two groups that are doing these experiments. They're doing the same experiment on a group of laboratory mice. And so the two different groups, they're doing the exact same experiment on the exact same mice. One group is getting slightly different results from the other group. And again, this is very puzzling. Same experiment, same kind of procedure, same mice. And this is kind of puzzled and stumped the researchers for quite some time. And then they kind of looked and looked at kind of the protocols. And so one group, they're selecting the mice at random. So all the mice have an ID, and so they have a computer. They pick the mouse. From the they pick a random ID of the mice, and then they go get that mice. The other group was randomly picking the mice by sticking their hand in the cage and then grabbing the first mouse that they grabbed. Now you may think that's random, right? I'm just picking, I'm just sticking my hand in and grabbing the first mouse I get. But it turns out that some mice are faster than others. They were consistently, when they actually looked at the IDs that they were grabbing, it was not a truly random sample. They were getting the slower, slightly larger mice, the ones that were not as quick. So you just have to be careful when the point of the story is just because you think you're sampling at random, right? Grabbing just any old mouse, you may not be, right? And so in this case, right, obviously the right thing to do is every mouse has an ID, and you're randomly using a computer or picking names out of a hat, will work just fine. Okay. And so if you can't figure out ahead of time what the population is and what the chance of the selection for each group of that population, then you don't have a truly random sample. From there is kind of the takeaway message from that. Okay, let's take a look at sampling. And so this is just kind of the nuts and bolts on how we will do sampling in our library. So here we have a data set, and this is flight time. So average delays of flight times from there. Okay, so we just load our table, and then the only thing we're doing to the table is that we're creating this row column. From there, and so we're just adding this row column, and then we're adding that to the table. And so this is just basically this is the index for the row, and then this fancy little thing, move to start, that just moves that column to the beginning from there. Okay, so we have the data, the flight number, the destination, and then the delay in seconds. Okay, and you can see that you can have a delay of negative seconds. That means a minute. Sorry, this is a delay in minutes. That this flight left 3 minutes early, and this one left an hour, 64 minutes, an hour and 4 minutes late. Okay, so kind of showing an example of a deterministic sample. So here we're selecting all of the rows that were landing in Newark Airport. EWR is the airport code for Newark International Airport. So that's deterministic. That is certainly not random. We get that table. And if we run this, if we ran this again, we're going to get the exact same table every time we run that, right? It's deterministic. Another deterministic sample is here. We're just taking a select number of rows from the table. And so we're taking the rows, right? We're going from zero up to the number of rows in the table. And then we're taking every thousandth, we're skipping, we're starting at 0. And then you can see row 1,000, 2,000, 3,000, so on and so forth. So right, that's deterministic. We're picking exactly those. And then, but that is a sample, right? That is a sample. We're not taking the whole population. We're taking every 1,000 rows from there. And just taking, some selection of there. That's also deterministic. Right. Every time we run that, we're going to get the same table back. Probability samples, and we can use random choice for this. That's going to be different. And so in this case, we're going to sample with replacement here. Oops, sorry. We are going to sample with replacement here. And so what we're going to do here is, remember, so how does choice work? Choice, we pass in an array, and it's going to pick one element out of that array. And so what we're passing in here is the number 0 up to, but not including the number of rows, right? That is going to give us the row index for the entire table. So here we're randomly picking a row in our table, And then this parameter is going to be how many times we're going to do that. Okay, so that's going to give us a table with 100 rows in it. And you can see there's our column. And if we run this again, every time we run this, here, every time we run this, we're going to get different output, right? If you look at the rows, it's going to be different every time. Okay, and so that's the default for choice. Is it's going to do sample with replacement, right? It's going to put that back in. We can also do sampling without replacement, and it's the same call to NP choice. We just add this optional argument, replace equals false. Okay, and so if we looked at if we took enough samples. If we took enough samples and looked at them, we would see that for the first table, it's possible for a row to be represented twice. Okay, without replacement, you're guaranteed that every row is going to be unique from there, but it will be random, right? So if we run this again, we're going to get a different row out of it from there. Okay. And the last thing here is, here's an example of a systematic sample where we are, see, what are we doing? We're randomizing the start, okay? So we're randomizing the start. But then once we've had the start, then we're going to pick every 1,000th row from some starting point from the first 1,000, okay? So it's kind of similar to the previous thing that we said where we're taking every 1,000th row. But here we're varying in that first 1,000 elements, we're picking a random point within that first 1,000 to start from there. Okay, so that's systematic, but it is random because if we run this again, we will get that differently. Okay. All right. Any questions? Any questions? Kind of how we take these samples? We'll get lots of practice with that. No? We're good? Awesome. Okay, so now that we know how to sample, now we can start thinking about distributions. And so what's a distribution? We're going to talk about probability distributions. And that is going to be some random quantity rather, that's gonna take on some range of various values associated with it. Okay, and so kind of give a concrete example. If we roll a 6-sided die, right? So kind of each one of those is an event. And if we look at a probability distribution, we can think about the probability of all possible values for the event, for the quantity, for example, rolling, right? And in this case, it's actually pretty straightforward to calculate the probability distribution, right? Rolling a 6-sided die, it's a fair die. The probability of each number coming up is going to be 1/6, right? So a probability distribution would be all the possible outcomes. In this case, the numbers 1, 2, 3, 4, 5, and 6, and the probability of each of those values. Okay, and so we can calculate that, right? We can calculate that if we can do the math. For this example, it's straightforward and simple. But many of the problems that we're going to look at, it's actually going to be pretty hard to work out the probability distribution. And so then we're going to fall to this idea of simulating this quantity. And that's going to be the approach that we're going to take. But, it's good to remember where kind of these distributions come from. And in the case of the die, right, we can calculate that from first principles. We can calculate the probability distribution. The other thing we can do is we can estimate, the goal here is to estimate that probability distribution through random sampling. Okay, and so if we can't directly calculate the probability distribution, Well, what we can do is we can look at empirical distributions. And so empirical basically means observed values, experimental. Okay. And so we can look at a distribution based on running an experiment, like rolling a die, flipping a coin, simulating the Monty Hall game. And we can observe what we saw, right? And so this is the Monty Hall example is really good because we kind of did both. We kind of calculated the probability distribution from doing directly by doing the math. But then we also simulated the game and got an empirical distribution, is what we did from there, right? Those are based on our observations. We ran it, 10,000 times, and we actually looked at the results from there, right? And we could do this from repeating an experiment. So if we run an experiment and we look at the distribution of all of our observed values, we call that an empirical distribution. And plotting it out as a histogram, that will give us the proportion of each value that appears. Okay. And let's see that in demo form. And while I'm setting it up, is that all? Any questions? Feel free. Okay. In this case, so let's look at the calculated and distribution and empirical distribution of rolling a die. And so how can we do that? Well, because we like operating in tables. So let's make a table. Let's make a die table that has one row for every possible outcome. Okay, so how will we do that? We'll create a table. We'll add a face column, the face of the die, and then we'll just set up our array going from 1 to up to, but not including 7. So we're going to have 1 through 6 here. Okay, and if we look at that, there's our dice. And so we can roll the dice by calling sample. And this will give us, that will roll the dice 10 times, and it will give us a new table of the outcome of each individual experiment from there. Okay, and so if we wanted to plot that, we're just setting up the bins for our histogram here. And so because each value is a whole number, and so just setting up the bins correctly, we kind of having it range from the first bin from 0.5 to 1.5 and so on and so forth from there. And you can see, so those are our particular bins. That's just setting up our bins to make our histogram look nice, right? And so if we calculate from first principles, so if we plot the histogram of the dice, right, the die table, remember the die table just had one outcome for all of our die faces. And so that is kind of the direct probabilities, right? We've made our histogram such that the width of each bin is going to be 1. And so if you look at the percent per unit, since the unit is 1, you can see that all outcomes are equally likely and that you have a 1/6 chance of getting each particular face. Okay. And so now, so that's kind of, right, that's looking at that kind of from calculating it. So we can simulate this, and we can get our own empirical distribution. We can get our own empirical distribution by sampling. And so if we sample 10 times and plot that histogram, we will get one particular distribution. Okay, and you notice it, well, first of all, it changes every time. So if we run it each time, you can see that it changes around, and it doesn't necessarily look like the distribution, the theoretical distribution that we'd expect. But we only did 10 samples. So I'm going to hide that output, and then let's run this a little more. Let's sample 1,000 times. Okay. If we run that, now we're starting to kind of look very similar. Now remember, each time we run it, we're going to get a slightly different distribution. But it's starting to kind of look like our theoretical distribution, our probability distribution, our empirical distribution is starting to look like the probability distribution. And now if we kind of turn it up to 11, and we run it, how many times? That's 100,000 times. That might take a little bit to pull through. Computers are fast, right? That's exciting. Notice how, if I hide this output, notice how it is starting to look a lot more similar. And so kind of the takeaway from this is that as we keep doing more and more samples, the empirical distribution will converge to the probability distribution. Any questions? All right, I think we've got 2 minutes left. I'm not going to rush through large random distributions from there. So, you know, in the remaining minutes, any questions?
All right, so last time before the break, I think Jason talked about topic 12, sampling. Okay, and in particular, we looked at, or you guys looked at with Jason together, looking at how sampling is done, as well as how to think about distributions. Okay, and we talked about probability theory in the past, like in topic 11, and then in topic 12, that's where we can start using all of the Python skills that we have learned so far, that we can actually realize those sampling and realize those distributions in Python and see how things work. Okay, so like I said, now I think with all of the skills and knowledge that we have accumulated by far, I guess, I think we're ready to talk about how we can make inference. Okay, so those are thinking about, well, we get data, we have some visualizations, we might have some interesting research questions that we want to answer. Okay, and now with all of that in mind, we can try to see how we can actually assessing any kind of research question that we have in mind. And then the first step to do that is what we call large random samples. Okay, so we're gonna walk through some of the results, and then we'll be talking about using the using demos. Okay, so let me make sure. Yeah, okay. So now we have knowledge about distribution, and then we know how to do random samples from Python, okay? And one important result that if you have taken some statistics course, you probably have heard about this law of averages, or what people call central limit theorem, is that if you can repeat experiment, okay, we call it a chance experiment, okay, if you can repeat it many times, like a super large number of times, and as you can see or have guessed, we're gonna use the for loops that we're able to do in Python to make this happen for simulation, okay? So we're gonna repeat experiment independently and under the same condition for a large number of times. Then the proportion of times that a particular event occurs gonna get closer to the theoretical probability of the event. Okay, so maybe this sounds a little bit vague, but a toy example we have over here is that if you are able to, especially in Python, if you imagine what we can do, right? You increase the number of rows of a die, like 6-sided die, and if it's a fair die, then we know that if we do this for a large number of times, the proportion of times that you're gonna see the face with 5 spots gets closer to 1/6, okay? And that's true for any of the numbers, 1 through 6 as well. And we wanted to show you that this is the law of averages, and we are going to use this general rule and general result to think about how we can make inference about certain quantities of interest, okay? So another thing to keep in mind is that, well, suppose you have a sample, okay, like a sample of observations, okay? If you have a large enough sample space, or if the sample size is large, then the empirical distribution of a uniform random sample resembles the distribution of the population, okay? So this may be with high probability, okay? So this might, again, sound a little bit vague, but what I want you to keep in mind here is that if you have a large sample with large sample size, okay? And then if I now take a uniform random sample, so remember we can do the random sample in Python. If I take a random sample in that way uniformly, like each record is having the same chance of being selected. If I look at the empirical distribution, okay, of that sample, then what we're gonna see is that if you have a large enough sample size, the empirical distribution of your sample actually gonna resemble the distribution of the population with high probability. Okay, so what this is telling us is that we wanted to make sure that we have large enough sample size, okay? And then if we do a uniform random sample out of it, we can get a distribution that will look very much like the population with high probability. And that can help us to determine, or if you don't have access to the population itself, this can help us approaching that. And then we can have high confidence that we're having a good distribution resembling the population. Okay, so again, the population, if you remember, it's unknown. Okay, we don't have access to it. Okay, but in a lot of cases, we have a sample. And then here we're advocating that if you have a large enough sample size, then Pinker distribution of that might look very much like that of the population. Okay, so with all of this in mind, okay, let me bring the first demo up, okay, and hopefully you will get to see how that is done in action. Okay, all right, okay. So large random samples here, okay, we are loading everything that we need, okay? So the data set that we're working with here is United Airlines from summer 2015, okay? We're looking at the date of the flight number, the destination of that flight, and also the number of minutes of delay, okay? So we're curious about this delay variable in this case, okay? So this is the last column over here, okay? And you will see that if it's 0, then it's right on time, okay? If it's a positive number, meaning that there's some delay. If it's a negative number, meaning that they arrive earlier than they scheduled, okay? So this is a numerical variable, okay? And then here, let's focus on how we can understand that delay variable a little bit through thinking about large random samples, okay? So here, as you can see, we have a really large data set. And in this case, we will take this data set as the population, okay? Because we have collected, assuming, okay, every flight, okay, in summer 2015, okay, we collected every data point. So this is the population, okay? We know that exists, okay? In this case, we do have access to it, okay? So now let's look at if we start to take random samples of that delay column, okay? And let's see how likely or how easy it is for us to see whether the sample going to resemble the population, okay? So that's the goal here, okay? So this is a pretty special case that we do have the population, and now we're using this as a demonstration to show how the sample resembles the population given certain conditions, okay? All right, so if we still keep working on the population for now, okay, I'm just gonna do certain visualization here, okay? So we have a delay by minutes, okay? And notice that I only get the bins of -20 to 201, just as the general, like the big bulk of the data will be in this range. But of course, some of the data points might fall outside of this, like the first one is delayed for 257 minutes. Okay, so there are, of course, more extreme data points. But here we're just showing a general trend, and you will see that it ends at 200, okay? All right, so that's one way to get a sense of how the population looks like. And of course, we can also return several summary statistics, like the minimum of this delay is -16, okay? The maximum, you can also do the mean, which is np.average, if you remember that. So it's on average 16.5, 0.6-ish minutes, okay? Delay for all of the flights in 2015 summer. And then we can also look at the median, okay? So all of this, so average and median, both of them are coming from the NP, so it's the NumPy package, and then the min and maximum, they're just regular functions here, okay? Yeah, no worries, yeah, feel free, like we're recording the lecture, so hopefully you are able to join much of it, but if not, if you still have Zoom issues, you can catch up with the video. Sorry, I'm just responding.
Thank you.
Yeah, thank you. All righty, okay, so this is the population, okay, keep in mind, okay, and we have several summary statistics of the population, okay, so keep those in mind that we are having access to the population so we can return all of this. Okay, so now let's begin looking at how we can take samples of things and then whether the sample size matter. Okay, so if you recall for this specific topic, we're saying that if the sample size is large enough, then the empirical distribution of the random sample that we can get going to resemble the distribution of the population with high probability. Okay, so we have, I think, a little bit more than 13, close to 14,000 observations in the population. Okay, so I'm demonstrating here of taking 3 different samples. Okay, the first one is size 10. The second one is size 100. Okay, the third one is a size 1,000. Okay, so before running all of this, which one, based on the empirical distribution that we're talking about earlier, which of the three you think going to have the highest probability resembling the population? Size 10, size 100, or size 1,000? Feel free to type in the chat or just speak up by unmuting yourself. Which one?
Size 1,000.
1,000, yeah. So like we know from that result, the highest, yeah, and thank you, Zach, in the chat as well. So not surprisingly, we'll see that soon. Okay, so notice what we're doing over here. Okay, so United is the data set, data table name. Okay, we're doing a sample. Okay, so this is what we learned, I think, from before the break. Okay, so then whatever goes into the sample parenthesis, the method over here, you type in the number of observations or the sample size that you're taking. Okay, so when we do this part, we're taking a random sample of 10 records out of that total population. Okay, and then we do histogram. Okay, this is just visualization. We're using histogram called hist method. Okay, on that sample that we generated, and then we select the delay column because that's the variable we're looking at, and then we're using the same bins as before. Okay, so this is trying to visualize everything in the same scale. Okay, so let's look at this one. Okay, so by the way, don't forget, this is what the population should look like. Okay, so when we say like resemble the population distribution, we're talking about a sample, hopefully, with higher chance when you have a larger sample size, it's going to look much more like this population distribution. Okay, so this is the first one. Okay, apparently we only took 10 observations, right? And looks like many of them are around 10, around 0-ish, and then around 50-ish. Okay, we only have 10 records, so that's why we are not able to explore the population distribution as much. Okay, now if we move to 100, okay, starts to look a little bit more like, right, the population distribution. Okay, not surprisingly, and if we get to 1,000, okay, you will see that overall it looks much more similar to the one of the population. Okay, so this result, well, hopefully intuitively makes sense to you. And then we verify using the demo that indeed, if we're looking at an empirical distribution of a sample, if you are taking a random sample out of population, and if the sample size is large enough or as large as you can get, then the sample distribution gonna resemble the distribution of the population with high probability. Okay, so this, I guess, a biggest takeaway out of this is that we want to make sure that we are taking random sample with large sample size in order to have a resemblance of what the population looks like. Okay, make sense? Sense, everybody? Okay, cool. So let me, new topic. Okay. All right. So the next one, okay, finally we get to talk about statistics. Okay. And this is a key, as you will see, how we are making inference about certain unknown quantity. Okay. So we're going to start with a few terminologies. Okay. And then we're going to bring back to demo again to see what kind of statistics are out there people like to make summary about, as well as how to get one step closer to making inference about the statistic. Okay. All right. So all right. So a statistic or several. So we're going to talk about them in generic terms and then look at certain examples. Okay. So for inferences, okay. So again, inferences are what we are trying to make based on a data set or code. So we have access to a data set, maybe a population, maybe a sample. But in particular, if you have the population, there is nothing to be inferenced about because you know the entire truth. Okay. More likely when we're talking about inference is that we don't have access to the population. We only have a sample, but we want to use the sample to learn something about the population. Okay. So in that kind of scenario, okay, you will see that, well, we talk about inference or statistical inference about making conclusions based on the data in random samples. Okay. And because in this case, the population is unknown. Okay. So what we're doing here, as we can see here, is that we use the data to guess the value of an unknown number from the population. Okay, it's fixed, consider as fixed, but it's unknown. Okay, we're trying to get an understanding of it. And what we have from a sample is that we can create an estimate of the unknown quantity. Okay, and then the estimate going to depend on the random sample that we take. And then of course, because each random sample that you take might be different from one another. So the estimate that you're getting is random. Okay, so I'm going to stay here for a little bit. Okay, let's just get those concepts clear. We have a population that we don't know certain thing about. Let's just say I'm curious about the mean. Okay, and I know the population exists out there. I don't have access to the entire population, but I want to know the population mean. So I'm trying to figure out the unknown mean. It's fixed out there. I just don't know it. However, I can always take a sample, or maybe a sample is already available to me, and I can create an estimate. If it's for the mean, the best one you can do is take the sample mean. Okay, so the sample mean is what we call an estimate of the unknown population mean. Okay, it depends on the sample, and then just like what we're seeing in Python just now in the Jupyter Notebook, the demo just now, right? We are looking at, well, just now we're looking at the sample size, how large it is can help us to know the larger it is, the more likely it's going to resemble the population, right? So just imagine the example that we did, like for size 10, size 100, and size 1,000. If I take the mean of each of the sample, because the sample with the larger sample size is going to resemble the population better, right? So if I take the mean of the sample size of 1,000, that means it's probably going to be a better estimate of the population mean than the sample size of 10 and taking the mean. Okay, so that's why earlier we wanted to know first about the empirical distribution of the sample comparing to the underlying true population distribution. Okay, because if the distribution resembles it really well, if I take any kind of statistic like the mean, the median, I don't know, the standard deviation, things like that, you will have a higher chance to resemble what's in the population that I'm curious about. Okay, so for us, keep in mind, when we're talking about inferences, we're talking about making conclusions based on data in random samples, okay? And what we're doing is that we're creating an estimate of the unknown quantity using the sample, and that is what we can do to have an educated guess of the unknown fixed number in the population. All right, a few more terminologies over here. Okay, we also call the number associated with the population as the parameter. Okay, so parameter is something unknown, but it's fixed, like mean parameter, median parameter. So that's another way we refer to those terms, okay? And statistic in particular, like the one that we're using over here, we refer it to a number that we calculate from the sample. Okay, so mean statistic, if we're talking about mean statistic, we're specifically talking about the sample mean. Okay, if we're talking about mean parameter, we're specifically talking about the population mean. Okay, so we differentiate those two as early as we can so that later on we know exactly what is known, what is unknown, okay, and what is that we're using to estimate what. Okay, so the bottom line again is that we want to know certain things about the population, but we don't know what it is. It's unknown, but it's fixed. What we're getting is sample, and then we're able to use sample statistic to estimate the parameter in the population. Okay, so here we also talk about another terminology, test hypothesis. Okay, so we're going to get to the detail of that later as well. Okay, but overall, you can see that a statistic can be used as an estimate of a parameter, like the mean example that we get just now, or it can be used to test hypothesis about how the data were generated. Okay, so hypothesis, again, we will get to it in detail, but in sum, we can also come up with statistic based on the hypothesis that we have in mind from the sample, and then we're able to use that to test them against the population as well. Okay, so those are the general terminology and framework that we're working with. Okay, and of course, now we know, okay, based on what we know about the terminology so far, we know we are using statistic to make estimate about the population parameter, okay? And if we can have a statistic from a sample, and we know now in Python, we can also take multiple samples, right? I can take a large number of samples from each of it. I can take a mean. So if I do that, I gradually get a probability distribution of the statistic. Okay, so pay attention to what we're talking about now, like the distribution, like moving from before about the distribution of the data points. Okay, now we're talking about the distribution of the statistic that we can calculate. Okay, so earlier, the delay variable in the United dataset that we saw earlier, when we were taking the histogram, if you remember, right, like from the population, that's a probability distribution of the observations, okay, each of them representing a data point, okay? And then when we take a sample, when we do a histogram of different sample sizes, 10, 100, and 1,000, those are, again, still distributions of observations, okay? Now we moved from that to what we were talking about of probability distribution of a statistic, okay? So imagine if I take the mean of a particular sample, I only get one mean, right? If I take another sample, I start to get another one. So what we're talking about here is that, well, if you're able to take a large number of samples and then from each sample, you're able to calculate the statistic, you start to get a distribution of the statistic itself, okay? So if you're only getting a population, if you're only getting a distribution of the observations, well, if you just take one sample and then you can graph it and then that's good enough. However, if I want to know about how the statistic, like the mean, going to behave, okay, what is the distribution of that? In theory, you have to take a large number of samples, okay? And then from each of them, you can get a mean statistic calculated. And if you visualize that, that gives you, so, okay, some terminology here. We call it as the sampling distribution or probability distribution of the statistic. Okay, so, and this is again coming from the fact that even though I'm only interested in the mean, every time I take a random sample, I take the mean, they could be different from each other. Okay, so depending on the sample that you take, the statistic going to vary. Okay, and because of that, we are able to come up with what we call probability distribution of a statistic. If we're able to sample a large number of samples, and then from each of it, we are calculating the statistic. Okay, so just keep things in mind. It is also distribution, okay? But we're specifically talking about what we call sampling distribution or probability distribution of the statistic. And in essence, we're trying to get all possible values of the statistic and all of the corresponding probability, okay? This could be hard to calculate, okay? Either you have to do the math, okay? And that's what, if you have taken a stats course, you probably have heard about, like I said, central limit theorem. So that's gonna guarantee under certain circumstances, you're able to know what exactly, say, the mean statistic gonna follow, what kind of distribution it's gonna follow, okay? However, in this course, like I said, maybe a few lectures ago, because we have the power of doing large number of samples that we're able to do, okay, especially through Python in our course, then what we are trying to do is that instead of doing the math and know exactly what the distribution or the probability distribution, sampling distribution of a statistic should follow, we're going to actually generate all possible fit samples, okay, and calculate the statistic based on each sample. Okay, so what we're doing essentially, as you will see in the demo in a second, is that we are going to generate large number of samples. From each, we calculate the statistic, and then we're able to get a probability distribution of the statistic because we are able to take a large number of samples. Okay. All right, so before we get to the demo, let me show you empirical distribution of a statistic. Okay, so notice that we started off, okay, talking about the sampling distribution or the probability distribution of the statistic. Okay, that's like in theory what could exist. Okay, if you're able to notice here, we're talking about all possible values of the statistic. Okay, however, in practice, well, I don't know, you can take 10,000, 100,000 samples, as many as you want if the calculation is feasible, computation is feasible. But since you're still like approximating what the true or underlying probability distribution is going to be, so we're still going to call what we're going to do through simulation as the empirical distribution. Okay, so again, if you remember what we defined earlier, empirical distribution is based on what you can sample. Okay, and so for us, we're gonna generate the empirical distribution, which is based on the simulated values of the statistic. Okay, it will consist of all of the observed value of the statistic, and then we're also going to know the proportion of times each value appear. Okay, so notice earlier on the previous slide, we're talking about in theory, right? We have a probability distribution of a statistic or a sampling distribution. That's what we call all possible values. Okay, but if you're doing it through simulation, you will only exhaust maybe part of the all possible values. So that's what we mean by all the observed values of the statistic. Okay, and then we're going to get the proportion of times each value appeared, which is going to give us a sense of the probability distribution. Okay. Lastly, we want to make sure that we're going to have a good approximation, okay, of the empirical distribution to the probability distribution of the statistic. In order to make that happen, we want to make sure that the number of repetitions in the simulation is large enough. Okay. All right, so a couple of things going on, especially trying to link what we talked about earlier. Okay, so here we're talking about the good approximation of the empirical distribution to the probability distribution of the statistic. The rule of thumb that you need to meet, like the criteria you need to meet over here, is that the number of repetitions in the simulation needs to be large. Okay, meaning that I have to repeat my experiment for a large number of times. Okay. Earlier, what we were talking about is that, well, you need to have a large enough sample size, okay, in order to have your distribution, your sample distribution to look very similar, right, to the population distribution. So these are two different things, okay? One is the sample size itself, how large the sample size is, okay? And that needs to be large enough to have a good resemblance of the population distribution. And the other thing we're talking about here is that if you want to have good approximation for the statistic distribution, okay, you will need to have the number of repeated samplings or the number of experiments to be large enough. Okay? So pretty much, if you want to have a good approximation, you will have large number of simulations as well as, well, I think so as well, that you need to make sure your sample size is not too small. Okay, because let's just say this. If I do like a sample size of 10, okay, we saw that before, right? Like the mean probably going to be way off from the population mean. Okay, so if I only have sample size 10, even if I repeat my sampling for 10,000 times, each of them might be far away from whatever the truth should be, right? So even if I can have a large number of repetitions, because my sample size is too small, I might still not be able to have a good understanding of the population mean. Okay. So keep those in mind together, and we will now go to the demo, which hopefully gives you a good sense of what we're trying to do. All right, okay. We're gonna go back to the United Airlines data set. Okay, so again, we have a population, okay? And then let's just look at the median. Okay, so the median, let me just show you, okay? The median of the entire population is 2 for the delay variable. Okay, but if I take a random sample, as I'm showing you over here, right, I use the sample method, and then I take the median of that random sample. Well, the sample size is only 10 over here, so every time I do a new one, it could be far away from what the population median is. Okay, so like the population median is 2, as we saw earlier. Okay, and now if I'm only taking a sample size of 10, if I'm doing that for many different times, as you can see that like most likely it's far away from it. And we knew that because the sample size might be too small in this case. Okay, but keep that in mind. We're going to use this general type, like the general format of the code to do the probability and the empirical distribution of the statistic that we're talking about. Okay, so we do np.median, right? That's how you can get the median. And then within it, we are taking a random sample first, right? And then select the array, like the particular column of delay using the dot column method. So we're getting it as the array, and then we take the median. Okay, so how about we wrap that up into a function? Okay, we call it sample median. Okay, the return is exactly what we just showed up here, except now size is the input of the function. Okay, so this sample underscore median method wrapped up what we just showed up here. So now you're able to, well, typing size equals to 10, so that can directly do that sample median for you. 2-step, right? The first one is take the random sample of the certain size that you input, and the second step is to get the median of it. Okay, so we wrap it up because later on you would imagine, I guess already, that we want to experiment with different sample sizes and see which one is giving us more information. Okay. All right, so keep that in mind. Okay, so to get us started, we have this sample underscore median method function. Okay, and what we're gonna do, so this is our old trend. Okay, we're using a for loop again. Okay, for loop here in particular, we started off with an empty array to save all of the sample medians that we're able to draw, right? And then second is that in the for loop statement, we're repeating this for 1,000 times. Okay, so what we're doing is that for I in AP.A range 1,000, so we know that this is going to do it for 1,000 times. Okay, each time I compute a new median based on the given size. Okay, in this case, the size is 10. Okay, and then I append it, right? Append the new median to the sample medians array that I created. So after running all of this, I will have 1,000 different sample medians based on size 10. Okay, so keep that in mind, like just have to get it straight. Sample size is 10, the number of repetitions is 1,000. Okay, so if I do this, like I said, you're gonna get 1,000 different sample medians of sample size 10. Okay, all right, so let's run that. It should be really quick. Okay, and then let's do a table with all of the visualization over here. Okay, so let's see what we have. Okay, so this is the sample medians. Okay, and this is a histogram, we know. Okay, we're using the bin of -10 to 31. Okay, and just to bring back your memory really quick, the population median is 2. Okay, so what we have done over here is that we have created an empirical distribution of the sample median. Okay, the reason is because we have taken a sample median every time we took a random sample. Okay, and then we come up with what we call the empirical distribution of the sample median, because we have repeated this for 1,000 times. Okay, each time we're repeating the experiment independently under the same condition, right? So this is exactly what we call the empirical distribution of the sample medians, given sample size 10. Okay, so 2 is somewhere here. Okay, not too bad, right? I mean, it's still like sort of in the middle of the sample medians, right? Like the population. And you will see later that we're going to try with different sample sizes that what's very useful about this kind of approach is that as long as we have a large enough repetitions, we're usually going to have the unbiased, or like say whatever the underlying population parameter going to be like in the middle-ish, okay, of the sampling of the empirical distribution that we're able to come up with. However, don't forget, we still have the sample size as something unknown or something is changing, right? And we talked about earlier that, well, if you have a larger sample size, the empirical distribution of the sample is going to resemble the distribution of the population with higher probability, right? So one thing we're going to see soon is that, yes, you can have different sizes as long as you have enough number of repetitions. You will get a good overall approximation to the sampling, to the probability distribution of the statistic. However, the sample size is still going to play a role. We're going to see how that comes into play, okay? All right, so what we have done here so far is that we are doing the sample median empirical distribution, okay, of doing it 1,000 iterations or repetitions and given a sample size 10, okay? So now let me do this. This is gonna run a little bit longer. Well, it's done already. But what this is doing, as you can see, is that I'm still repeating this experiment for 1,000 times, okay? But right now, I'm bumping up my sample size to 1,000, okay? Earlier, only have 10, okay? Now I have 1,000, okay? So the histogram of this new graph, okay, is much more concentrated, okay? So hopefully you can see both, you know, here. This is when the sample size is 10. That's the empirical distribution, right, of the sample, like the empirical distribution of the statistic, where the statistic is the mean. Down here, this is also the empirical distribution of the statistic, the median statistic. But here, the sample size is 1,000. Okay, so what this is telling us is that, yes, for each of these 2 experiments, I'm doing 1,000 repetitions. Okay, so that condition is met, right? We know that we're going to have a good approximation, so that's good. So both of this are approaching what we call the sampling distribution of the median, okay? But they do look very different, right? It's the same range as we're showing over here, okay? So both of them are approaching their own, okay, sampling distribution, but their own sampling distribution is different because the sample size is different, okay? So imagine we talked about earlier that when we have a larger sample size, the distribution of the sample resembles more, right, of the population distribution. So if I take the mean, or take the median in this case, of a size 1,000 versus a size 10, I think for the size 1,000, we're going to have a median that is closer to the truth, okay, because it's more likely, right? So what these two are showing us really is that, well, first of all, we need to make sure that we have enough number of repetitions. Okay, 1,000 is definitely good enough, okay? And then the second is that depending on the sample size, we're gonna have, if the sample size is small, we're gonna be centered at 2, that's good, but we have a wide spread of possible values, okay? Because the sample size is small, it's possible that sometimes I get -5, sometimes I get 30, okay? Just because the sample size is small. However, if I bump up the sample size to be 1,000 and I still repeat this experiment for 1,000 times, then most likely I'm always going to be around 2 if you look at this, right? Because there's only 4 bits over here. So I guess it's 1, 2, 3, 4, okay, when the sample size is large. Okay, so as we know, when the sample size is large, we're going to have a sample distribution resembles more of the population distribution. So if I take any kind of summary statistics, right? If I take a statistic out of it, I will have a higher chance to resemble more of the true or of the unknown. In this case, it's known because we know the population. But if we don't know the population, then this also gives us guarantee, right? That if we're able to have large enough sample size as well, then everything gonna work better. Okay. So lastly, for this part, this is going to take some time to run, so I should be sending this to run. And what we're doing here is that I'm trying with sample size 10, sample size 100, okay, and sample size 1,000. Okay. For all of them, I'm doing 2,000 iterations, okay, or repetitions, and I'm trying to come up. Like I save all of them into their own sampled median, and then I want to graph them together just to show what we were talking about earlier. Okay, like regardless of what you're gonna get, as long as you have large enough repetitions, the sample median will always be centered at the population median. Okay. However, depending on the sample size, you will have different results in the spread of the distribution. Okay. So let me do the plotting over here. Okay. And I will pause here for a second just to give you some time to digest this. And since if I put it into breakout room, you won't be able to see it, so I probably will refrain from doing that. But maybe I will pause here. Yeah, let me just pause here for a little bit, okay? And I want you to think about what is the difference and the similarity between the 3 different histograms, okay? And okay, comments, thoughts about the differences and the similarities between the 3 different histograms here and why? Maybe similarity first. Seems that they're all pretty much concentrated around 2, okay? And especially, I guess, when size 1,000 and size 100 over here, okay? When the size is only 10, the mean is probably centered maybe around 1-ish or something, maybe a little bit left, okay? But overall, it's around what the population median was, okay? So that's what we're saying, that if we're able to repeat this experiment for a large number of times, regardless of the sample size, you will be getting on average what the population median is, okay, or what the population parameter is, okay? And the differences, I guess, here will be that the sample size 1,000 is much more peaked, right? You have many more incidents of more concentrated between, I guess, 1 to 4-ish, 1 to 5 over here. Whereas when you have size 1,000, you have a wider range of possible values, okay? And then when you get to size 10, you have an even wider range of possible values. So remember, for the 3 histograms over here, all of them we have repeated for 1,000 times. Okay, so the number of observations in each of the histogram is the same. It's 1,000. Okay, but now we can see that the height is much more taller for size 1,000 and much more concentrated around the true population median. Okay, and that's what we mean by if you have a large enough sample size, okay, you will have less variability of your sampling distribution. Okay, if you have a small sample size, okay, like -5 to positive, like 20-ish, okay, that's where you're having a much wider range of possible values. Okay, So to bring this back to what we were talking about earlier about parameter as well as the statistic. Okay, so in this particular example, the parameter of interest is the median. Okay, we're looking at the median of the delay variable. Okay, and in particular, we do have the true median because we know the entire population. Okay, so parameter again is what we use to describe the unknown thing that is in the population. Okay, for our example here, we happen to know it because we happen to know the population. Okay, but in many cases, if you don't have access to the population, the parameter is the unknown but fixed quantity that we're trying to make inference about. Okay, however, whenever we have a sample, okay, in this case, we have the population, so we can generate a large number of samples. Okay, but sometimes you might not be able to do it. But regardless, whatever you can calculate for the parameter of interest on the sample, we call them statistic. Okay? So we're always trying to use the known but random statistic that we can calculate on the random samples. We use them to make inference about the unknown but fixed quantity parameter in the population. Okay, so those concepts could be foreign at the beginning. Okay, so if we come back to this slides one more time. Okay, yeah, so this again, I will recommend going back to the slide one more time later on after class as well, just to make sure that for those concepts that we're talking about inference, we do differentiate what we mean by parameter and statistic. Okay, and generically we say that parameter is a number associated with the population. Statistics is the number that you calculate from the sample. Okay, but for specific examples in the demo just now, we're talking about the median. Okay, we talk about the parameter, median parameter in the population and the median statistic in the sample. Okay, so we use these terminologies because later on you will see that we will be interested in many other parameters. Okay, so mean is another parameter of population that people will be interested in. And of course, if we redo everything we did over here with the mean, I'm pretty sure everything will work just fine as well. Okay, just for a variety of demonstrations, we did this median. But it could also be that the parameter of your interest is maybe like the standard deviation, for example, of the like say of the delay variable, okay? Or maybe even the minimum or maybe the maximum. So all kinds of stuff that you're curious about for the population, we call it as a parameter. Okay, it's unknown but fixed. Okay, statistic is once you take the sample, you're able to know it for sure, right? Because you can take the sample, you can take the mean, take the median, take the standard deviation, et cetera, et cetera. But we have to account for the fact that every time you take a sample, whatever statistic that you calculate can be different, okay? And that's why we care about probability distribution of a statistic, and then moving on through simulation to talk about the empirical distribution of the statistic. Okay, all right. I think that's all I have for this topic, but I'm happy to answer any clarification questions before we move on. Anything else? Feel free to type in the chat or just speak up. Anything. Okay, all right. Okay, sounds good. So let me start.